Hello everyone. Welcome to the lecture 1. Today I will be discussing about the problems related to introduction to a spectroscopy. To study the spectroscopy, we need to understand some of the fundamental. Like, let's see. The first thing is, what is a spectroscope? If you talk about a spectroscopy, it's simply the interaction between light and matter. Okay. To understand the spectroscopy, we have to understand the light, what is the property of light, how can we calculate the energy of light, what is the frequency of light, what is the wavelength of light. Similarly, we have to understand about matter. What is the structure of matter, how the energy levels are distributed inside the matter, those things. Then only we can understand the interaction between matter and light. First, let's focus on light. Light is an electromagnetic wave oscillates in space like this. Here you can see it's kind of wave. The top one are called crests and the negative one called troughs. And the length of a complete wave is called wavelength. And this height is called amplitude of the wave. So this the energy of this electromagnetic oscillating waves can be given by this equation. E is equal to h nu, where nu is nothing but frequency of light. Okay. Like how fast the wave is oscillating per second is called frequency. Let's try to see here. I will draw two situations. 1, 2. Okay. So there is only one wave at this time. So let's say this is a time axis. In the second case, we have two waves. Like it's oscillating faster than the first case. Meaning in 1 second, how many waves are there? 1. How many waves are there? 1, 2. Total number of waves 2. Here total number of waves 1 wave. So we can say that the frequency of this oscillating wave is higher than this oscillating, and this frequency can simply be related by this equation, c by lambda, where c is velocity of light, okay, and the lambda is wavelength, length of a complete wave, and this wave number is defined by 1 by lambda. The inverse of wavelength is called wave number. So by using these equations, let's try to calculate, let's try to solve some of the problems. The first question is, what change in the molar energy in Joule would be associated with an atomic transition giving rise to radiation at 1 Hz? So let's say you have one atom has a nucleus and has some fixed orbit, electron. Some atomic transition is taking place. Meaning, let's say electron is going from here to here. Okay. And this giving rise to radiation. So it went back here, then again it will come back to this. Okay. Let's say we irradiated some light. Let's see. So this transition happened. And again during relaxation time, it's giving radiation of 1 Hz. Giving radiation of 1 Hz, that is frequency of radiation is 1 Hz. 1 Hz is nothing but per second. Okay. So frequency is given. Now this question is asking energy. To calculate energy, energy is equal to h nu. Now it's asking molar energy. Molar energy, that is energy of 1 mole of radiation. So we have to multiply with Avogadro number NaH nu. So Na is 6.022 10 to the power 23 per mole. Okay, and what is your 6.626 10 to the power minus 34 joule second. And what is the frequency? 1 per second. So this per second is cancelled out, and we are getting something. Calculate it. So 6.022 6.626 39.9 10 to the power minus 11 joule per mole. Okay, so we are getting some 3.99 10 to the power minus 10 joule per mole. This is your energy. Okay, so this is your answer. So the per mole energy associated with the radiation is this much. Okay, now let's come to the next problem. Next problem is the prominent yellow line in the spectrum of sodium vapor lamp has wavelength of 590 nanometer. What is the minimum accelerating potential is needed to excite this line in an electron tube containing sodium vapor? So what is the minimum energy required to excite this electron? Okay, excite this line. So what is given? Lambda is given, wavelength. So 590 nanometer. So 590, let's convert into meter. Will be 5.9 10 to the power minus 7. Now you have to calculate energy. So energy is nothing but your hc by lambda. Okay, so what is h here? Planck's constant. It will be 6.626 10 to the power minus 34 joule second. 3:2 meter per second. What is lambda? 5.9 10 to the power minus 7 meter. This meter is cancel out. This second is cancel out. So we got something 3.37 10 to the power 15 34 minus 15 minus 90 joule. Okay, this is almost. Now let's come to the next question. This question is, assume that 10 to the power minus 9 joule of light energy is needed by interior of human eye to see an object. So what is the energy? This energy is required to see some object. Okay, so energy is 10 to the power minus 17 joule. How many photons of green light, and lambda is also given, to the lambda 495 nanometer. So we'll convert into the SI unit. So 495 10 to the power minus 9 meter, 4 10 to the power minus 7 meter. Okay. Now the question is asking is, how many photons are needed to generate this minimum energy. So you have to write this equation: N H C by lambda. Now this is your number of photons. This N is your number of photons. Okay. So N can be calculated by E lambda divided by Hc. Okay. Now energy is given 10 to the power minus 17 joule. And what is your wavelength? 4.95 10 to the power minus 7 meter. Planck's constant is 6.626 10 to the power minus 34 joule, and velocity of light is meter per second. So this meter is meter gone. This joule gone. Here is joule second, so this second is also gone. Now you will be getting something 4.95 divided by 6.626 divided by 3, 0.25. Okay. Now coming to the unit. So on the top 24, 70, 32. It's 10 to the power 2. Okay. So you need 25 photons. Now coming to the next question. So these are the some problems based on light's property, like how we can calculate the energy of light, how we can calculate the wavelength. Similarly, you can calculate, there are a lot of questions based on this concept. Okay. Now coming to the next thing about material, how we can understand the material. So we understood about the light. So detail of this light, you can refer to the recorded lecture of the fundamental of spectroscopy on NPTEL. You can search it on YouTube. Okay. So I'm solving here just the problem based on the concept discussed there. Okay. Now coming to the material part. To understand the material, we need to know the structure, how the electrons are distributed, how the energy levels are distributed. To know that, we need quantum mechanics. We used here quantum mechanics, and this is required in the later of this course. Okay. So again, I'm not discussing the concept here in the detail, because the concepts are clearly explained in the detail in the lecture note. So based on the detailed discussion, I am solving some problems. Okay. So the first question is, if psi xt is the wave function of particle again this C is particle, so we are talking about matter. Okay. So initially we understood about light. Now we are trying to understand about matter, and then we will understand about light matter interaction, and that is spectroscopy. Okay, so that's our goal. So the question is, particle moving along x-axis at the instant time of t. Okay. Then psi star xt multiplied by psi xt dx is, so you know psi is some complex wave function, complex function, I will say, it does not have any physical significance. But psi square, which is given by psi into psi star, represents probability. Probability. Okay. Now this psi is time dependent. This psi here is called wave function, is time dependent here. So this multiplication psi star x t psi x t dx will represent the probability within this small volume. Okay, it's not a volume, it's a one dimensional motion. So I will say within this small position at time t. Okay. If you are not multiply with any small position or any small volume, then this psi square will represent probability in the entire space. If you multiply with some small position or a small volume or a small area, then this term will represent the probability in this small interval. Okay, in this small interval at time t. So this will be your correct option. Correct, fourth one. Now coming to the next question. So the function fx equal to e to the power I kx, where k is a constant, is the eigenfunction of linear momentum operator. What is the eigenvalue? So we know that, let's say there is some operator A, applying on some function f, we are getting some value b and fx. This is your eigenvalue. So this is your condition. Okay. Now what is the operator here? What is A here? Operator is your linear momentum operator. Linear momentum operator. So that is nothing but I minus I h cross d by dx. Okay. And what is your function? Fx equal to e to the power I kx. So we need to solve for this one. I h card d by dx to the power I kx. So you will get its differentiation. Okay. So you know the differentiation of d by dx e to the power ax is equal to a to the power ax. So we take out the coefficient of x. So here also we will take out the coefficient of x, ik, and then again the same function. So this I become I square plus k kx. Okay. So the value of minus I square is minus 1. H cross I kx. Okay, so you will get something h cross k for I kx. So it's h cross fx. See, this is your b. This is your eigenvalue. Okay, so we see the correct option first. Now coming to the next question. The question is, a quantum particle which can move in one dimension is described by the wave function this. So the wave function is psi equal to c to the power minus 5x. Okay. The normalization constant c, if the particle is confined only positive values can be of one dimension along x-axis. So along positive axis. Okay, so this is your 0, this is your x-axis. So it's moving along positive axis. Okay. So how can we solve it? So first write normalization condition. What is that? It's n equal to 1 by under root psi star dx 0 to infinity. Let's try to solve it. Okay. So here n is nothing but your c equal to 1 by under root 0 to infinity so we already took out the c, like we have to write this one, this expression 0 to infinity c e to the power minus 5x c power 5x dx equal to 1. Okay, c square 0 to infinity minus 5x dx equal to 1. C square is 1 by 0 to infinity, this will be cancelled out into 1. Now the unit will be e to the power 0. Okay, so you'll get something like 1 by 0 to infinity dx. So you'll get something 1 by x 0 to infinity under then 1 by infinity minus 0. So 1 by under infinity. 1 by under infinity is infinity. So any of the value is possible. Now next question. So next question is this one, commutator. So let's take some function fx. and the commutator can be defined as x cube px minus px x cube, and px we know that x cube minus I h cross d by dx, okay, minus I h cross d by dx. Okay. Now let's try to apply on some function. So you can write x cube ex on some f x. So I'll directly write this one x3 minus I h cross d by dx minus minus plus sorry h cross d by dx x cube fx. Okay, now let's try to solve this. So we'll take this x cube minus I h cross d by dx fx d by dx x cube multiplied by fx. Okay, now this one we are getting I h cross x cube d fx by dx, and this one we are getting here if we have minus sign minus I h cross, so here it to be, so we can write 3 x square fx plus x cube d fx by dx. Okay, and one I h cross will come here, so this whole term will be cancelled out. Okay, whole term will be cancelled out. We will get some I h cross, we can write h by 2 pi. Okay, 2 pi, and here you will have 3 x square fx, so we can take out this fx from here, and then you will get something. So we have I in the downside, so we have to multiply I up and down, so we can write I square h 3x square by 2 pi, so we will get minus 3 h x square by 2 pi I. So first one is your correct option. Okay, now coming to next question. So again, these are the problem we are solving based on the material. So we are treating particular material using quantum property. So this thing you can refer to the lecture note for the detailed discussion there. Okay. Now for next question you can see here. So there are two wave function given, psi1 and psi2 for a particle in a one dimensional box. So we have one dimensional box. Length is 0 to d. So inside the box we have potential V. Outside the box so the question is psi1 is normalized but not orthogonal to psi2. So we need to solve two problems here. First is problem 1. We need to see 0 to a normalization condition. Is the first equation satisfying normalization condition or not? So we need to solve psi1 star dx is coming 1 or not. Okay, first. Second condition, 0 to a psi2 star dx is 1 or not. Third one, 0 to a psi1 psi2 dx must come 0 or to be orthogonal. Okay, so we will solve first, second, then third. So the first one is your 0 to a psi1 star dx. Okay, 0 to a, what is the value of psi1? So 1 by b sine pi x by b. 1 by b sine pi x by b. Okay, so that we can take 1 by b sine pi x by b. So the whole thing we have conjugate dx. So the complex conjugate of this is same as this one. So there is no need to change anything. We don't have iota term. So this term will be multiplied by this. We would have 1 by a, which is a constant. We can take it out, and then sine square pi x by b dx. So 1 by a sine square we can write you can simply write 0 to a 1 minus cos 2 pi x by a, okay, divided by 2 dx. So we use this relation. Sin square theta is nothing but 1 minus cos 2 theta by 2. Okay. So for solving this, you will get something 1 by a, so I'll write first integration, so I'll write 0 to a 1 by 2 dx minus 1 by 2 0 to a sine, sorry, cos 2 pi x by a dx. Okay. So this one you will get a by 2 and from here you get some minus sine 2 pi x by a divided by 2, this whole term per, so you will substitute this here, this whole term will go to 0. Okay. This whole term will go to 0 because you will get something like sine 2 pi minus sine 0, and sine is your periodic function. So at 0 your sine will be 0, at 2 pi your sine will be 0, at pi at sine will be 0, at 3 pi, 4 pi. So here you pi, 2 pi, 3 pi, 4 pi, like sine and pi is 0. So that the second term is 0. So you got something. This is equal to 1 by 2. This here will be cancelled out. Not equal to 1, which is not equal to 1. So from here we can write not equal to 1, psi 1 is not normalized. Okay, the first option is incorrect. Got it? Now coming to the second option, psi 2 is normalized. So let's check the normalized condition of psi 2. Okay, so 0 to infinity, problem number second. So directly write 2 by a sine 2 pi x by a. Correct? So it's not a, it's b. B here b, 2b sine 2 pi x by b dx. Okay, so you got something 2 by b 0 to b sine square 2 pi x by b dx. Okay. Now let's try to solve this. So we have 2 by b 1 minus cos 4 pi x by b divided by 2, 0 to b. Okay, like 2 by b, so the integration shifts here to b, so we can write 0 to b 1 by 2 dx minus 1 by 2 0 to b cos 4 pi x by b dx. The second term will go to 0 as I discussed in the previous slide. So we have this term only, so you will have 2 by b divided by b by 2. You got 1. Okay. So psi 2 is normalized. The second is correct option. Why? Because in third one saying psi 2 is neither normalized nor orthogonal. You don't need to check this one because psi 2 is normalized. So this is incorrect. Okay. No need to solve this. Okay. Now coming to next problem. problem based on particle in 1D box. So for a particle in a one-dimensional box where the particle is confined between x equal to 0 and x equal to a. If the particle is in the stationary state, a stationary state means the probability of finding the particle in that state, it is not changing with time. Okay, corresponding to n equal to 2, the most likely position can be found. So there are two ways to solve this problem. First, you can simply plot and you can see how. Let's try to plot it. So we will draw one dimensional box. Okay, so it's asking n equal to 2, n equal to 2, n equal to 2. So number of node in one dimensional box, number of node is n minus 1. So 2 minus 1 is equal to 1. Node means the probability of finding particle would be 0. Okay. So we have one node. So graph should look like this. Correct. This is your maximum. See, this is your wave function. This is your psi. This is your psi. So let's plot psi square. Okay. This is your positive. This is your negative. So when you will do a square, your both terms will be positive with higher magnitude. Okay. So this box is not that accurate, but I will try to draw with higher magnitude. Okay. So this is your position, n equal to 2. So at the center, at a equal to 2, probability I'm describing with p equal to 0. Okay, and in the half, this is 3 a by 4, and this half, this is a by 4. At these two position, we have the particle will be, you can say, the most likely position for the particle. Okay, so this is the correct option. Sorry, this is your correct option. Third, so simply by plotting, we can understand the most likely position for the particle. But let's say we don't know how to plot it. Then how can we solve it? We can solve it by writing equations. How? Let's try to do that. Okay, so for n equal to 2, what is psi? Psi is your 2 by a sine 2 pi x by a. So I am not solving here in detail. You can find psi square. Psi square represent probability. Okay, so you'll get something 2 by a sine square 2 pi x by a. Okay, I'm considering this, let's say z, for maximum. For most likely position means the question is asking to calculate the maximum. For maximum, dz by dx equal to 0. You will get something dz by dx equal to 0. By using this condition, solve for x, you will get these two values. Okay. So there are two methods. If you don't know how to plot, then you can calculate by this method. If you know how to plot, then you can solve very easily within a minute. Okay. Now coming to next question. For a particle in a one-dimensional box where the particle is confined between x equal to 0 to x equal to a, if the particle is in the stationary state, okay, the average momentum of the particle is equal to. So Let's draw a box here. 0 to a particle is n equal to 2. And how can we calculate some average value? How can we calculate some average value? So how can we calculate some average value? Let's say one observable A, some observable A, and the average of A can be calculated as psi A psi. Simply we can write it here for momentum, average momentum Px, we will say is minus I s cross d by dx. So you can calculate it 0 to a psi star px psi dx. Okay, so we can write 0 to a, what is psi here? 2 by a sine 2 pi x by a. The middle we have minus I s cross d by dx. And here 2 by a sine 2 pi x by a dx. So you can take out something minus I h cross 2 by a, and then you will have 0 to a sine 2 pi x by a here 2 pi a, sorry, 2 pi cos 2 pi x by a dx. Okay, so we'll cancel out this. Sorry, no, to no cancel out. Minus I h cut 2 pi by a square, and writing 0 in 2 sin 2 pi x by a cos 2 pi x by a dx. So I'll be writing this 2 sin theta cos theta is equal to sin 2 theta. So leaving it here and solving for this 0 to 8 sin 4x by x by u. So we can write so this is 0. Okay, so you get some first first. Simply you can use the odd and even function analogy, you can make it 0. Now come to next question. So for a particle in one dimension where the particle in confined position between the ground state, the most likely position. So for n equal to 1, this is a ground state. Because for n equal to 0, energy will be 0. So n equal to 0 is not allowed. So we can take this one. We have n equal to 1. So number of node n minus 1. So it will be 1 minus 1 equal to 0. Is no node. So you can plot like this. So you have maxima here in the middle. So what is this value? Nothing but u by 2. Or else you can solve by this one, writing psi 1 by a sine 2 pi x by a sine pi x by a. Then you can calculate psi square. You can say this z. Then you can calculate dz by d is equal to 0. Solve for x. Okay, second method. This is method 2. This is your method 2, and this is your method. Now coming to next question. So the average momentum in any state will be 0, because of the word function analogy. So you can use the same analogy as I solved above, and you can solve this question. Okay, if you have any doubt, you can write in comment section. Okay. So I'm not solving this question. Now next question. A unit of h square 8 ml square. The energy difference between level corresponding to 3 and 2 node eigenfunction. 3 node implies by n equal to 4. 2 node implies by n equal to 3. Okay. So n equal to 3, n equal to 4. So for n equal to 4, we can write energy. General formula of energy is n square 8 and n square. So we say this E4 16 x square and E3 we say 9 square 8 and n square. Now asking energy difference, meaning E4 minus E3. So 16 minus, then I will take this common, it will be 7 in the unit of h square 8 and n square. So the answer will be 7 in this unit. Okay. Now coming to next question. So the last one, the some transition. For this we will try to understand some of this concept. Einstein coefficient. There are 3 coefficients. So it's B12, B21 and B21. Okay. So this coefficient represents your spontaneous events, and again you can refer to the lecture note. You will see in the detail. Spontaneous emission means, for emission means a particle coming from higher energy state to lower energy state does not require any light. This is called a stimulated emission. Stimulated requires light. And this is your absorption. This is your absorption. Okay. So simply your B12 is equal to B21 is equal to B. We saw that this is again principle of detail balanced. So we solve for this one. We got some A by B. It's nothing but 8 pi H mu12 cube C3 cube. Let's say you have 2 states here. This is E1, this is E2, and the we can draw like this. This is your transition absorption. This is your stimulated emission, and this is your spontaneous emission. So we can write B21, B21, B12. Okay. B12. Okay. Now you can find the net rate, overall rate equation, or overall rate change in the particle. So those things you can calculate here, like d n1 by dt. N1, that is particle will go from here to here. So the number of particles is decreasing here, so you write minus equal to dnt by dt. This case is called saturation condition. Okay. So this is in case of absorption. In case of emission, we need to write dn2 dt minus sign. These things are discussed there in detail, and just briefing it out here. If E2 will be greater than E1, in this case, where N2 will be greater than, smaller than N1, and then absorption will take place. Okay. When N1 equal to N2, in this case called saturation condition. We will read this thing in detail in NMR. We will apply this saturation condition in NMR. Okay. what are the techniques we will use there to remove this saturation condition. Okay, those things we will detail there. Okay, and this distribution, this molecule particle distribution can given by this Poisson distribution. So N2 by N1 is equal to, I think what here, E2 minus A1 dot K. Okay. And third one is to take any transition from a state P1 to a state P2, the transition dipole moment. First of all, this transition can be treated using time-dependent perturbation theory. Secondly, the transition dipole moment for the transition from a state P1 to a state P2 must not be equal to 0, otherwise there will not be any transition. So transition dipole moment, I will write something like some tau here, initial state to final state is defined as 2 pi, because these are constant. This is your equation is psi f dipole moment, or you can write V dipole operator. I am just writing psi I is a square. This thing should not be equal to 0. This thing will be explained in detail in second week. So you to know what is transition dipole moment, how can we calculate transition dipole moment for a system, how can we treat it, you should refer to week 2 lectures. Okay, so this from this summarized lecture, let's try to solve some of the problems. So the first question is, which of the Einstein coefficient represents the probability of spontaneous emission? So you saw there the A coefficient. So emission means coming from, let's say I'm writing this as state 1, this is state 2. So emission means particle has to, I'll write an energy diagram. Particle will come from here to here. So emission, the coefficient, A coefficient is represent emission. A21 represents transition taking flow plus 2 to 1, not from 1 to 2. In case of emission, this N2 has to greater than N1, so the particle will come from 2 to 1. So this is your correct option, and A12 is incorrect. So the first option is correct. Okay. Now coming to next question, how does the B coefficient influence the interaction of light with matter? First is, it determines the probability of multi-photon process. It is irrelevant the probability of absorption. This is correct option. So B represents here both. So B represents both for absorption and emission, correct? And it represents a single photon absorption. Okay. Third question, what is the necessary condition of laser? So in laser, population inversion happens. And when this will happen? When N2 will be greater than N1. Okay. So this is your state 1. This is your state 2. Okay. In this case, so this is your current option. The last question of this session, the question is, what does the principle of detail balance state? The absorption and stimulated emission occur via different mechanism. the principle of detailed balanced state. Okay, the probability of absorption and stimulated emission are same. Molecule in the ground state can reach the cycle state spontaneously. There is a process with coefficient. This is a correct option. Both are same. Which one? Your absorption coefficient B12 and stimulator here B2. So this one we call principle of detailed balanced. So with this, I am stopping this lecture here. I hope you enjoy this. If you have any question, please let me know in the comment section. Thank you.